Episode 11 ended with a new problem. We now have two copies of the controller for high availability. Both look at Checkout app at almost the same time. Both see that 3 pods are desired and only 2 are running. So both reach the same correct conclusion. 1 pod is missing. But what happens if both act on that decision? Running 2 replicas is normally a good idea. If one controller process crashes, the other is already there to take over. The problem is that without coordination, both copies can watch the same object, read the same state, calculate the same missing work, and send a write at nearly the same time. This is a race between 2 individually correct decisions. The repeat safe reconcile loop from the earlier episode is still important. It makes sure that checking the same object again later does not cause the wrong action. But here, we have a different problem. 2 controller processes can look at Checkout app at almost the same time, and both can see the same old state before either one makes a change. So even if each controller is safe on its own, we still need a way to stop both from acting at the same time. A simple analogy makes the race easier to see. Imagine a shelf that should contain 3 boxes. 2 workers look at it at the same time, and both see only 2. Each worker correctly decides that 1 box is missing. If both place a box on the shelf, we end up with 4. The calculation was correct. The missing piece was coordination. Kubernetes controllers commonly solve this by electing one active leader. Both controller replicas are still running, but they compete for one leadership record. The winner performs the protected reconciliation work. The other replica stays ready, but waits instead of acting at the same time. The leadership record is a Kubernetes lease object. You can think of it as a small note that answers 3 questions. Who currently holds leadership? When did that process last renew the lease? And how long should the other replicas trust that ownership before trying to take over? At startup, both controller replicas try to acquire the same lease through the API server. The lease itself has a version, so competing updates cannot both quietly become the same next version. Controller A wins the update first and stores its identity as the holder. Controller B sees that leadership is already held and waits. After the election, the 2 replicas have different roles. Controller A runs the protected reconciliation work because it holds the lease. Controller B remains healthy and ready, but it does not run that same protected work. This gives us high availability without deliberately letting both copies act at once. Leadership is not permanent. The active controller has to keep renewing the lease. Each successful renewal tells the other replicas that the current leader is still alive enough to keep control. So leadership is continuously maintained, not granted forever. Now suppose controller A crashes. Its renewals stop. Controller B does not take over immediately, because a short network problem should not create a second leader too quickly. B waits until the old lease can be treated as expired, then acquires it and becomes the new leader. It may seem that once we have one leader, the problem is solved. But there is still a small chance of 2 writes reaching the API server close together. For example, the old leader may have already sent a request that gets delayed in the network. Meanwhile, another controller may become the new leader and send its own update. A user or another controller may also change the same object at the same time. So leader election reduces the chance of concurrent actions, but every write still needs its own protection. Here is a concrete failover race. Controller A reads Checkout app at resource version 900 while it is still leader. The network becomes unstable and A loses leadership. Controller B takes over and reads the object too. Then an old delayed write from A and a newer write from B both reach the API server. This is where resource version becomes a write safety check. Both controllers read version 900. Controller B updates first, so the stored object moves to version 901. When controller A later tries to update using the older version 900, the API server rejects that stale update with a conflict instead of silently overriding the newer state. Think of resource version like a numbered form. Two people both receive form number 900. Person B submits a change first, so the office creates form 901. When person A later arrives with a change based on form 900, the office says, "This copy is old. Read the latest form and decide again." A conflict simply means the object changed before our update was saved. So the controller should not send the same old update again. Instead, it should read the latest version of the object, check what still needs to change, and then send a new update only if it is still required. In short, after a conflict, the controller starts again from the latest state. For an update to an existing Kubernetes object, the pattern is simple. Read the object and remember its resource version. Change only what you intend to change, then send the update with that version. If nobody changed the object first, the update succeeds. If someone did, the conflict forces the controller to reread. But our missing pod is a create operation, and creates have a different problem. Before the new pod exists, there is no pod resource version to compare. Two controllers could both decide to create the same missing child. For that case, stable identity becomes another important safety tool. Suppose the missing pod always has the same name, checkout app 2. Both controllers may try to create that same pod at almost the same time. One request succeeds, and the pod is created. When the second request reaches Kubernetes, it sees that checkout app 2 already exists. So Kubernetes rejects the second create instead of creating another pod with the same name. The second controller should then read the latest state and continue from there. The retry behavior is the important part. An unsafe controller sees a failed or uncertain create and invents another new child, which can produce duplicates. A safer controller retries the same intended child identity. If that child already exists, the controller checks the latest state and continues from there. Deletion can also become tricky when things change very quickly. Imagine the controller sees a pod called pod A and decides to delete it. Before that delete request reaches the API server, the original pod A is already removed. Then Kubernetes creates a new pod with the same name, pod A. Now the name is the same, but it is actually a different pod. So the controller should make sure it is deleting the exact pod it originally saw, using that pod's unique identity, not just its name. Even after leader election, concurrency does not disappear from the system. One leader may run several workers so different objects can be reconciled in parallel. The work queue normally avoids giving the same key to two workers at the same time inside that queue. But users, other controllers, and other automation can still update the same Kubernetes object. That is why conflict-safe writes remain necessary. We can now separate the three protections clearly. Repeat safe reconciliation makes the same object safe to check again. Leader election decides which controller replica should actively run the protected work. Conflict-safe writes protect the cluster if two actors still reach the API server with competing changes. Each mechanism solves a different problem. Now replay the episode 11 problem with all three protections in place. Both controller replicas start, but leader election chooses controller A. Controller B waits. A reads desired 3 and current 2 creates the one stable missing child, and the cluster reaches 3 pods. There is no second active controller creating another child. Now make the test harder. Controller A creates checkout app 2, but its reply is lost and it then loses leadership. Controller B takes over. B reads the latest state and sees that 3 pods already exist, so it does nothing. And if the old create is retried with the same stable name, Kubernetes reports that the child already exists instead of creating a 4th pod. For a highly available controller, the practical setup is straightforward. Run multiple replicas, enable leader election, give every replica the same election identifier for that controller group, and allow them to read and update the lease object. Unrelated controllers should use different election identifiers so they do not accidentally compete for the same leadership record. In production, we also want evidence that tells us what kind of concurrency problem we are seeing. Useful signals include the current leader identity, lease renewal failures, leader transitions, reconcile retries for 109 conflicts, already exists responses, and write latency. Those signals help separate failover problems from normal write contention or faulty controller logic. The full model is now clear. First, reconciliation must be safe to repeat. Second, leader election chooses which controller replica should actively run the protected work. Third, the API writes themselves must detect stale updates or duplicate creates. Leader election decides who should act. Safe writes protect the cluster when timing still becomes uncertain. But there is one more problem. The same Kubernetes object can be changed by different people or controllers at the same time. For example, a user may change how many pods should run. At the same time, the controller may update how many pods are actually available, while another automation adds a label or annotation. These changes are all valid, but they affect different parts of the same object. So how can each one make its change without accidentally removing somebody else's? In the next episode, we will compare full updates with patches, see why status is often written separately from spec, and explore how field ownership lets multiple actors safely share one Kubernetes object.